linear speed and angular speed, two ways to measure rotational and circular motion. When discussing how fast an object moves in a circle, we can explain how fast an object is moving using either the linear velocity, which is how many meters of an arc length the object travels around the circle every second. Symbol V, meters per second. This is the same thing as speed. We talked about this entire year. We just call it linear speed to make it sound different from angular velocity. Angular frequency for circular motions. How many radians of an arc angle the object travels around the circle every second. For this, we use the symbol omega. It's not a W. It's more like a saggy butt cheeks or a sad-looking W. Radians per second, rads per second. Linear speed is length over time. So to calculate linear speed, we can use the length around a full circle, called the circumference, and the time around a full circle, called the period. So velocity is distance over time. The distance you travel is the circumference of a circle, 2 pi r, divided by the time that it takes to go around one complete circle, which we call the period. Because period and frequency are reciprocals, we can also say that v equals 2 pi r times f, because t is in the denominator. Angular speed is angle over time, so to calculate angular speed, we use the angle of a full circle, 2 pi radians, and the time around a full circle, the period. So omega equals the change in angular displacement over the change in time, and the angular displacement is going to be 2 pi divided by the time it takes to go full circle, the period. Because period and frequency are reciprocals, we can also say that omega equals 2 pi times the frequency. There's a three-sided equation, probably, on your equation sheet. These equation sheets are changing at some point. Just know that it's there. It's more useful if you don't need the equation sheet, of course, but, you know, can't remember everything, right? So this equation relates period to angular velocity and also to frequency. So if you were needing any combination of these, whenever you have a three-sided equation, you can take any two things, and there's an equal sign between them, so you can use them as needed. So you can say t equals 1 over f, or you can say 2 pi over omega equals 1 over f, if you don't have the period. And let's say you needed the angular velocity, but you only were given the frequency. You can just use this portion of the equation. That's allowed. Anytime that ever pops up again, like up here, you can say change in energy equals work, or you can say change in energy equals FD cosine theta, if that's more appropriate for the situation. Remember how length is related to angle by S equals R times theta. Let's say we divide both sides by time, so one side gets length over time, and the other side we get the angle over time. Length over time is speed, angle over time is omega, V equals R times omega. Remember how speed is V equals the distance you travel around a circle, the circumference, and omega is 2 pi over t. We can regroup the speed equation into V equals 2 pi over t times r. The 2 pi over t is the same thing as omega, so we get V equals omega times r. So as long as we measure angles in radians, we have a nice equation, V equals omega times r, that relates linear speed V, the number of meters of length traveled around the circle every second, to our angular speed omega, the number of radians an angle travels around the circle every second. The two animations show 4 objects making different circular motions. On the left, we've got 4 objects with the same linear speed v, because they go the same distance every second. Note the streaks are the same length. On the right, all 4 objects have the same angular speed, because they all make the same angle every second. On the left animation, where the objects have the same linear speed, which object has a greater angular speed? Red object, because it makes more angles per second. For the red object, V equals big omega times little r. So r is large, r is small, and omega is large. Meanwhile, if you go to green, you have a much bigger r, so that means because they have the same linear velocity, the angular velocity would have to decrease. So the green object, v equals tiny omega times big R. Looking at the right animation, where they have the same angular speed, which object has the greatest linear speed? Not omega. The green object, just by looking at this, you can tell travels a greater distance every second, which is our linear speed. This should be a v, not an omega. For the red object, v equals omega times r. R is small, so that means the velocity is small. Omega stays the same. For the green one, omega is the same. We have a bigger r, which means we have a bigger v. Here we've got gears turning with interlocking teeth. Which gear has the teeth moving the greatest linear speed v? Might be able to just look at that and see, looking at the dots on them. All three gears have teeth moving the same linear speed. All the teeth are going the same meters every second. That's why the teeth interlock. They move the same linear speed past each other. That's what's happening in any kind of gear situation. Are they traveling the same angle? Or same angular speed? Excuse me. No. Green has the highest angular speed because it's rotating a larger angle every second. Notice the smaller radius for the green compared to the red or compared to the blue. Because v equals omega times r and all gears have the same v, green has a smaller r, which means it has a greater omega. Green has a smaller r, which means it has a greater omega. Red has a bigger r, so that means our omega becomes smaller, which is why red makes less angles every second. Specifically, red has 3 times the radius of green, so red takes 3 times as long to make a full circle. Get it? Blue has twice the radius of green, so blue takes twice the amount of time as green does. You can try a stopwatch if you like. These 3 wheels are rolling down the street. The camera follows the wheels, so the world, represented by the gray grid in the background, and the street with the blue stripe, or bright stripes, is shown moving past the wheels. Yes, it is. Which wheel has a center of mass moving with the greatest speed? All 3. Same speed. I think you got that correct. The speed is the center of mass v related to the radius of wheel r and the wheel's rotational speed omega. By this equation, v equals omega times r. Again, which wheel has the greatest angular velocity? Same linear speed, so which has the greatest angular velocity? V equals omega times r. And v is the same, so that means the smallest radius is going to have the largest angular velocity. For the red, v is the same, tiny omega, big R.